So in the previous lesson, we found a formula for the determinant of matrices of sizes 2 by 2 and 3 by 3. We also indicated that those results can be generalized to compute the determinant of n by n matrices. In this lecture, we'll introduce a recursive approach through the theorem that we're about to introduce. It is recursive because it involves computing determinants of smaller sizes until the problem reduces to evaluating determinants of 2 by 2 matrices, which we already know the formula of. That is, if we've got the following matrix 2 by 2, a11, a22, a21, a12, then the determinant is just a11, a22 minus a21, a12. That is, we do the difference of the cross products. So the theorem states the following: let m subscript ij be the determinant, I forgot the b here, so be the determinant of the n minus 1 by n minus 1 submatrix of A formed by eliminating its ith row and jth column. So for example, if I've got the following 3 by 3 matrix, then m23 is the determinant of the matrix obtained by eliminating the second row and third column. We're left with 1, 5, 1, 0. So that's what M23 is. Then the determinant of the n by n matrix A is defined by the what we call first row Laplace expansion. It is this formula that you see over here. Now what we see here is an interchanging of sign between the different products of the Laplace expansion. This is what we saw in the previous lecture actually. We saw that we grab a row, let's say the first row, and that's why it's called the first row expansion. And we'll talk about if we could choose other rows. I mean, why is it only the first row? Why not the second or the third or the last one? Let's focus on the first row. And minus 1 to the power 1 plus j, if you let j run from 1 till n, you're going to see that minus 1 to the power 1 plus 1, that is to the power of an even number, is a plus, then a minus, then a plus, and so on, right? And then you multiply each term, a1j, by m1j. That is obtained by eliminating the row where a1j is sitting at and the jth column, that is the column where a1j is sitting at. You obtain a determinant of a matrix with one size less, right? Now, a question that might arise, could we form the second or the third or even the last row Laplace expansion? Well, of course you could. And it turns out to be that this guy is equal to j from 1 till n. We can replace the 1 that you can see here by, say, I. Simple as that. I for the row. I plus j, aij, mij, for all I in 1 till n. Okay, let's do an example over here. So, say I've got the following matrix. That is 1, 2, minus 1, 0, 4, 1, and 3, 5, minus 9. And the question is, what is the determinant of A? Well, using the first row Laplace expansion, we can write this as minus 1 to the power 1 plus j, a1j, m1j, right? Where j is going from 1 till 3. In that case, we can say we've got a minus 1 to the power 1 plus 1, a11, m11, plus minus 1 to the power 1 plus 2, a12, m12, and the last one for j equal 3, right? Now minus 1 to the power 1 plus 1 is a plus 1, so we get an a11, m11, and so on, minus a12, m12 plus a13, m13. What is a11? It's 1, so we get m11. What is a12? It's 2, minus 2, m12. What is a13? It's minus 1, so minus m13. Now the question is how to obtain m11, m12, and m13. As in the definition, mij is the determinant of the smaller matrix, submatrix, obtained by eliminating its ith row and jth column. So m11 is obtained by eliminating this guy and this guy, right? So we're left with 4, 1, 5, and minus 9, the determinant of that matrix. So 4, 1, 5, and minus 9. Now the vertical lines that stand for determinant. Minus 2, determinant of the matrix obtained by eliminating the first row and second column. We're left with 0, 1, 3, and minus 9, and minus m1, 3, which is obtained by eliminating first row and third column. So we're left with 0, 4, 3, and 5. Now let's compute those determinants. This is 4 times minus 9 minus 5 times 1, which is minus 36 minus 5 minus 2 into 0 times minus 9 minus 3 times 1. That is minus 3, and minus 0 times 5 minus 4 times 3, that's minus 12, right? This is equal to minus 41 plus 6 plus 12, which gives us minus 23, right? Now another question would be, could we have done this using the second row? Well, of course. Let's see how. So I'll do this here. So using the second row, and we'll see why it's easier on the second row in this particular example. So the determinant of A on the second row would be the sum j going from 1 till 3 minus 1 to the power 2 plus j, a2j, m2j, okay? You'll see that you'll get minus a21, m21 plus a22 m22 plus a23 m23, right? Note that a21 is 0, this is gone. a22 is 4, so 4 m22, minus a23 is 1, so m23. This is the reason why it's easier. The more zeros you have in a row, the easier the calculation of the determinant becomes. Why? Because a 0 will eliminate a computation of the determinant. So a 0 times a determinant computation, which is gone. You no longer need to compute m21. That's what it means. The best thing, if you obtain a row of all zeros, this is a theorem where, it's not a theorem, well, it is a theorem, okay. It is a theorem. So there's a theorem that actually tells you if there's a row with all zeros, then guess what? Your determinant is 0. It's not hard to see that while computing the determinant using the Laplace expansion by choosing the row of all zeros. Why is it 0? Because my ij's will be all zeros for that row, and hence the determinant is 0. So the more zeros you have, the easier it becomes to compute a determinant. Keep this important remark in mind. Anyways, we continue. What is m22? It's obtained by, so 4 times m22. What is m22? It's the determinant of this matrix. 1 minus 1, 3 minus 9, minus m23, which is obtained by eliminating the second row, third column, is 1, 2, 3, and 5. Computing this, we get 4 into minus 9 plus 3 minus 5 minus 6. This guy is minus 6. We're left with minus 24 plus 1, which is a minus 23. Hence, we got the same determinant using different rows, right? Well, as practice, you can compute the determinant using the third row and verify that you get minus 23. Another example would be on the following remark. So this remark might come in handy someday. Given a square matrix, the determinant of A is equal to the determinant of A transpose. Let's see this through an example. So let's say I've got A, which is 1, 0, 2, 1, 2, 5, and 3 minus 1 and 1. Computing the determinant of A would be to, let's pick the first row. So using the Laplace expansion, minus 1 to the power 1 plus j, a1j, m1j. That is a11, m11 minus a12, m12 plus a13, m13. a12 is 0, a11 is 1, so we're left with m11 plus 2m13, right? What is m11? It's a determinant of a 2 by 2 matrix, and m13 is also a determinant of a 2 by 2 matrix. Well, m11 is the determinant of which 2 by 2 matrix? Obtained by eliminating first row, first column, we get 2, 5, minus 1, and 1. Likewise, m13 is obtained by eliminating first row, third column. We get 1, 2, 3, and minus 1. Let's compute those 2 by 2 determinants to get 2 plus 5 plus 2 into minus 1 minus 6, right? That is 7 minus 14, which is minus 7. Now, same question, compute the determinant of A transpose. So A transpose would be 1, 0, 2 Remember, rows become columns. 1, 2, 5, and 3, minus 1, and 1. Right? So pick the first row, or if you want the second row, right? Because it has a 0 over here. And let's compute the determinant. So determinant of A transpose. Now, there's going to be a notational abuse, that is, aij represents the ijth entry of A. Well, here, aij will be used to represent the ijth element of A transpose. So in this case, we're saying aji is aij, just to remain consistent with the Laplace expansion, okay? So minus 1 to the power 2 plus j, because I picked the second row, a to j, m to j, right? So we get minus a to 1, m to 1, plus a to 2, m to 2, minus a to 3, m to 3, right? A to 1 is 0, a to 2 is 2, a to 3 is minus 1. So m to 2 is the determinant of this guy, 1, 3, 2, 1, and m23 is the determinant of this guy, 1, 1, 2, 5. Computing the determinants, we get 2 and 2, 1 minus 6, plus 5 minus 2, that is minus 10, plus 3, which is minus 7. Hence, the determinant of A transpose is the same as that of A, right? One theorem which we already stated up while solving the example is when we have a row with all zeros, then this means that the determinant is 0. The proof of that is fairly straightforward. I'm going to mention the proof in one sentence. Apply the Laplace expansion formula on the all zero row, and that's it. The proof is done. Okay? An example on that would be, let's say A is the following matrix: 0, 0, 0, 1, 0, 1, 5, 4, 10, 5, 0, 1, 2, 6, 8, all zeros, and 1, 2, x, y, 1 over pi. The determinant of this matrix is 0 because fourth row is all zeros. Now another determinant that is very easy to evaluate is that of a lower triangular matrix, or an upper triangular one, right? Because the determinant of A is A transpose. The lower triangular matrix, let's say L, is of the following form. So A11, then all zeros, then A21, A22, then all zeros. So everything that is above the diagonal end components is all zeros, right? It turns out that the determinant of L is nothing other than the product of its diagonal components. That is A11, A22, down to ANN. Very easy to compute. It consists of multiplying only the diagonal components of that matrix. So a remark here would be, based upon this observation, determinant of a lower triangular matrix is the product of its diagonal components, so the product of a.k.a. Same thing, the determinant of an upper triangular matrix is also the product of its diagonal components, a.k.a. And a particular case on those two matrices is if we combine those two results, is the determinant of a diagonal matrix. I'm not sure whether we mentioned what a diagonal matrix is. If we did, that's good. And if not, well, it is a lower and upper triangular matrix at the same time. What does that mean? It means that everything is 0. So the diagonal matrix is a matrix that is 0 everywhere except the diagonal components, which are possibly 0. An example of a diagonal matrix is the identity, where all its diagonal components are 1 and everything else is 0. Now this result of lower upper diagonal matrices is easy to prove. You can prove it by recursion, induction, using the Laplace expansion. I'm not going to do it here. It's very easy to do. Trust me. Now let's do a small example. Now a lot of students make a mistake over here. I'm going to pass it as an example so that you can keep it in mind. Let's say A is alpha I, right? Alpha I. Alpha is a real number. I is the identity matrix. So A could be written as alpha down to alpha, right? Everything else is 0. Question is, what is the determinant of A? Which is the same as saying the determinant of alpha I. Now using this, the correct answer is to multiply alpha with itself n times. We're multiplying the diagonal entries. How many alphas do we have? N alphas. So it's alpha power n. Do not do the following mistake. This is not equal to alpha because it's a scalar determinant of I. If you say this, then determinant of I is 1 and you're left with alpha. And alpha is not alpha power n, okay? So this is wrong. So that means that we cannot extract a factor outside the determinant. However, an interesting remark on the property of determinants is the following useful fact. The determinant of a product of two matrices is the product of the determinant of those two matrices. So that AB is that A times that B. We will not provide a proof, but we will be using this result numerous times without even mentioning it as a result, because it's very important. Another example would be to compute using the definition the determinant of an upper triangular matrix. So we're going to pick the row with most zeros, the third row, and apply the definition. So the determinant of A, 3 for third row, 3 plus j, j going from 1 till 3, a3j, and m3j, right? We get a31, m31, plus a32, plus a33, m33. a31 is 0, a32 is also 0, a33 is 2, multiplied by m33, 1 minus 9, 0, and 4, which is equal to 2 into minus 9 minus 0, that is minus 18. Now let's try to compute the determinant using the property that since A is upper triangular, then the determinant of A is the product of its diagonal components. So k going from 1 to 3, a, k, which is a11 times a22 times a33, right? Which is equal to 1 times minus 9, which is minus 18. And hence the property is correct. And hence we obtain the same solution. Now let's define a term that will turn out to be useful in computing the inverse of a matrix, and thus the term cofactor. The ij cofactor of A, denoted by C subscript ij of A, or simply Cij if we're talking about one matrix, it is nothing other than minus 1 to the power I plus j times mij. And thus, the determinant could also be expressed in terms of cofactor, right? So instead of saying j going from 1 to n times minus 1 to the power I plus j for the ith row, so applying Laplace on the ith row, multiplied by aij times mij, we can combine this mij with this minus 1 I to the power I plus j to get the sum of entries aij times the cofactor Cij. Also, we can define the adjoint of a matrix, that is denoted by a dj of A, which is simply the transpose of the matrix of cofactors. So it is the transpose, I'll put a transpose over here, and the matrix of cofactors is just a matrix containing the Cij's, right? So the Cij's over here, I'll just stack them in a matrix, C11, C12, down till C1n. Same thing over here, so Cn1 till Cnn, which is at the same time applying the transpose. You will see C11, C12 till C1n, C21, C22 till C2n, Cn1, Cn2 down till Cnn. So an example on the adjoint, computing the adjoint, would be given the following matrix A, which is 1, 2, 3, 4, 5, 6, 8, 8, and 9. Using the definition, the adjoint of A is the transpose of matrix of cofactors C11, C21, C31, as such. Now we know that each cofactor, Cij, is nothing other than minus 1 to the power I plus j times mij, where mij is the determinant of the submatrix A obtained by eliminating the ith row and jth column. So we start C11. C11 is minus 1 to the power 1 plus 1 multiplied by this matrix, right? 5, 6, 8, 9, which is 5 times 9 minus 8 times 6, that is minus 3, right? Minus 3 in the first entry. Likewise, C21 is minus 1 to the power 2 plus 1 multiplied by this matrix right here. So the determinant of 4, 6, 8, 9. 4, 6, 8, 9, that is 6. So 6 here. Continuing in the same spirit, we get minus 3 right here, 12 right here, minus 15, 6, minus 8, 8, and minus 3. So this guy is the adjoint of matrix A. Notice that if we come and multiply A by the adjoint of A, what happens? Go ahead and multiply A, that is 1, 2, 3, 4, 5, 6, 8, 8, 9, with the adjoint, that is this matrix right here, minus 3, 6, minus 3, 12, minus 15, 6, and minus 8, 8, and minus 3. Do the multiplication, and you will get minus 3, 0, 0, 0, minus 3, 0, and 0, 0, minus 3. What is this? It is minus 3 times I. In other words, if we divide both sides by minus 3, we get 1 over minus 3 times A times the adjoint of A is the identity. Rearranging a bit, you're going to get this scalar multiplied by the adjoint instead of A. You will get A times minus 1 over 3 times the adjoint of A is the identity. Well, what is that matrix over here? What is it? Let's try to compute the determinant of A. We didn't look at the determinant yet. Now let's go ahead and compute the determinant just for a while to see if we can see where this minus 3 is coming from. So the determinant, using Laplace expansion on the first row, and in terms of the cofactors, could be written as A1j times C1j. That is A11 C1 plus A12 C12 plus A13 C13, right? That is replacing, we get 1 times C11, which is minus 3, plus 2 times 12, plus 3 times C13, that is minus 8. You get minus 3 plus 24, minus 24, which is minus 3. So the determinant is found in the denominator over here. So we can actually say that A, in general, you can say the following. It's not only for this example. So you can say that 1 over the determinant of A times the adjoint of A. This matrix over here, if you come and multiply it by A, you will always get identity, given that the determinant is not 0. Okay? So what does that mean? It means this guy is the inverse of A. So we got ourselves a new theorem. It's not a new theorem, no. This is something well known, but this is an established theorem. So given a matrix A that is invertible, then the inverse of A is 1 over determinant of A times the adjoint of A. And that's why in the previous lectures we mentioned that the determinant of A, to test invertibility for the inverse of A, the determinant should be non-zero. If it's 0, then 1 over 0 is infinity, and hence the inverse does not exist. So an example on that would be find the inverse of the matrix A in the previous example. 4, 5, 6, 8, 8, 9. We have everything. We know the determinant, which is minus 3, and we know the adjoint, which we just computed. So plugging everything in, 1 over minus 3 times the adjoint of A, which is minus 3, 6, minus 3, right? It's over here. Multiplied by, and 12 minus 15, 6, and minus 8, 8, and minus 3. Okay? So this guy is the inverse of A. So in this one, we talked about expansion by minors to compute the determinant of any n by n matrix. Expansion by minors is a simple way to evaluate the determinant of small size matrices, right, by hand. For large values of n, the method is not practical, even though it's recursive, but we will see that it is very useful in proving important results. We wrote down a formula, a recursive formula, using this theorem, and the equation is referred to as the Laplace expansion. First row Laplace expansion because we wrote it down explicitly for the first row. Now you can generalize for any row by simply replacing the 1 by the row index I. In the formula, we saw the Mij, that is a determinant of a smaller size matrix, by eliminating the ith row and jth column, denoted by Mij. We gave some examples on that. Even though we didn't emphasize on the term Mij, the Mij term is called the minor of the matrix, corresponding to the ith row and jth column of the matrix. Now, expansion by minors is a recursive process, as we saw, and the determinant of any square matrix is just a linear combination of the minors, right? By continuing this process, this formula will lead you to determinants of size 2 by 2, which are easily computed using the cross formula if you want. So here 1 times 0 minus 1 times 5, right? Some important properties on the determinant include that the determinant of a matrix is the same as the determinant of the transpose of the matrix. Also, the determinant of a product of matrices is equal to the product of the determinant of each matrix. We saw an important theorem that says if it happens that a row of a matrix is all zeros, then the determinant of that matrix is 0. We saw determinants of specific types of matrices that are lower, upper, triangular, and the diagonal matrix that is both lower and upper. In that case, for those three matrices, the determinant is nothing other than the product of the diagonal entries of that matrix. We also introduced the cofactor corresponding to the ijth entry of matrix A. That is just the minor multiplied by either a plus or a minus, depending on the power I plus j. We saw that we could express the determinant instead of the minors in terms of the cofactors of that matrix. So the determinant is also a linear combination of the cofactors of the matrix. We introduced the adjoint of a matrix, that is nothing other than the transpose of the cofactor matrix corresponding to A. Last but not least, through an example, we saw that we can write the inverse of a matrix as 1 over determinant times the adjoint of that matrix.